All right, howdy again, Mr. Hardy here. We are actually coming near the end of Unit 2 already, believe it or not. A little bit shorter than Unit 1 was. So today we are going to be graphing radical functions. A little bit high there we go. And you're going to start to notice what I'd mentioned before when we were doing the absolute value graph. You're going to start seeing a pattern develop here. I kind of gave you a sneak peek that I wrote up here at the top of your page. When we're graphing radical functions, we're going to see a similarity between this and what we're about to start. So, quick flashback. When we were doing the absolute value functions, we were graphing those. We always talked about how our left or right shift was in here, okay? And it was the opposite of what we would think. So left was plus and right was minus. And then our K was our up-down shift, but it followed the rules more with what we'd expect it to do. And then I didn't write it on here, but then we had A in the front, which determined our stretch, okay? Did it get skinnier? Did it get wider? Did it reflect over the x-axis when it was negative? So now we're going to put that to use with another type of graph. So earlier, if this was our function, okay, this absolute function x minus 2 in the absolute value, minus 3, would be which two directions is what we're actually asking. Well, the minus 2 would be right 2. And then the minus 3 on the outside would be down 3. Okay, so similarly, if this is my parent graph, we talked about parent graph before, it's just the plain old, before it was the absolute value of x, now it's the square root of x. Same thing, because what you're going to notice is this. If I take my first dot here, okay, my first spot from the origin, and I shift right 2 and down 3, I end up in the same spot. Okay, if I find another spot, again, that goes through the crosshairs, and I do the same thing and I go over 2 and down 3, I end up in the same place. And we've got one more right here, over 2 and down 3. The graph has just been shifted, okay? Shifted where? Right and down. So when we talk about transformations, again, that's a fancy way of saying, which way are we going to shift? What's that going to be for each of these? And the transformations here are the same as they were for the absolute value graphs. Nothing different. So when I'm doing these, I go, oh, so it's right and up? Yeah. Right 1, up 2. But we have to notice everything. So like, for instance, when I get to number 2, I notice my regular shifts, okay, opposite of what I would think here. So left 3, always left and right inside. Minus 4 is down. But this time I have one more transformation. I have that negative on the outside. Now I can't just say stretch 1, okay? Why? Because the negative, as we saw before, flips or reflects my graph about the x-axis. Now, if you were to write or say something to me, if you were right here talking to me and you said, well, it flips it, I would understand what you're talking about. The issue is going to be when you're doing it on an online type quiz, the option is going to be reflect about the x-axis. It's not going to say flip. So we got to get that terminology down. Okay? And then now, number 3, I would actually ask you for a moment to pause me. And I want you to try to write the 3 transformations down on your own. Hopefully at this point you paused me. So we've got the opposite of what I would think there. So we got left 4, we got up 3. Now this time it's not reflecting, it's not negative, it's just stretching by 5. In that case, it's actually getting skinnier. Because with these, it's the same thing. It's going to get skinnier. I need to hold off on some things here. I need to quit taking on things we haven't talked about yet. Okay, so that's just it for now with our transformations. So when we start graphing, and I am going to pull something else into play here momentarily, get that here ready. So the equations y equals the square root of x and y equals the cubed root of x. Again, we always assume if we don't see a little index or root number in there that it's a 2, but we're going to be dealing with 3's as well. So we're going to graph these. Again, if you don't have a calculator of your own, remember that we've got the app that you can put right on your netbook that's right in there. And let me do this too. So I had people ask this in the chat the other day, and then I was like, so we've got our Chrome app that is on Mr. H's library on his classroom page, way at the bottom. Way at the bottom, there will be this thing called an emulator. Okay, I might reference that again here at the end. We'll see. And then if you're on phones, okay, if you're on iPhone or the iOS system or something like that, Mr. H likes Calculate 84. Okay, it basically is the exact same stuff as on here again, same button presses and things like that to help you out. And then if you are in Android world, there's a little more work to this one, but it pays off because it's the same thing. And no, I'm not misspelling things. It's called Wabbit Emu. Is the best Android one that I've found, but I always have students looking. So if you ever find one for Android that is just like having the calculator here, please shoot me an email or message me or something so we can get that updated. So those are your options if you don't physically have a graphing calculator. Okay, let's get down to business. So here, we're going to go back to y equals. If there's something in there, make sure you hit clear to clear that out. And then we've got y. You're like, okay, how's square root work? Okay, square root, I'm going to hide this, is going to be second and the x squared button. You see in blue right above there the radical sign. So second and square root will get me x squared. And then I just want the square root of x. And we're going to graph it. Now we want to see what it looks like. I'll move this out of the way at this point. Okay, got this curve here. Now let's go to the chart, which again is second in graph. And you're going to see all these error messages. Now I'm going to talk about those in a second. What I'm interested right now in is jotting down all of the whole number pairs I can see. So I see 0, 0. I see 1, 1. I don't care about all the decimal-y stuff. Again, method to Hardy's madness. Just stick with me. 4, 2, 9, 3. Okay, let's go ahead and plot those. 0, 0, 1, 1, 4, 2, 9, 3. And I want to make mention of a few things with the graph now that we've got those. Okay, first thing with the graph, it starts here, goes out, and that's going to keep going forever. That gets an arrow. This does not. This does not keep going forever. Well, how do I know that? Let me go back to the chart. Once I go beyond 0, 0, I get all these error messages. You're like, yeah, why are you getting all those error messages? Can you take the square root of a negative? Not yet. You're like, what? That's for later. We'll chat about square roots of negatives later. But for now, no, I can't take the square root of a negative. So my graph can't go into that area. It stops right here. So whenever you're getting ready to start one of these, you can see where it starts, just wherever the error messages stop. That's where my graph starts. Okay. Domain and range. Reminders here. Domain, x values from left to right. Okay. And if I look at my graph, it starts here at 0. And goes up. There's my arrow forever to the right. Okay. My range. My y values from bottom to top. Okay. Here's my bottom, still at 0, just on the y-axis. And even though you're not sure, I mean, you even look at it on here, it looks like it just flattens out. It's still very slightly increasing forever. And I'm not going to give you a little trick yet, because tricks are for when we got things down a bit. But there's even a trick for figuring out domain and range before we even see the graph. Okay? Now, we'll chat about that shortly. The other one we're going to have is the cubed root of x. Now, this is just Mr. H talking, and this is a good way for us to practice something we just got done with. When we were going from a radical to an exponential, okay? Because here's something you're going to notice. There isn't a real quick way, simple way to get a cubed root on your calculator. So here's my suggestion. We know there's always an exponent of 1 on things when we don't see them. And if I wanted to write this as an exponential, I would write exponent over root. I would prefer that you put this in your calculator that way. So like when you go to put this in, instead of trying to find the cubed root button, there's ways around it, but man, it's more button presses than I care to deal with. We're going to do x. This little up arrow, this is called the caret button. This will make your exponent. And then just type in your 1/3 and graph it. Get out of the glare there. So it kind of looks like there's a snake slithering through our screen. So when I punch this up, I'm like, okay, again, looking for whole numbers when we can. X, Y. All right, let's look around a bit here. Okay. So you're like -8, -2. Now, Hardy, where did you know how to start there? Like if I wouldn't have scrolled up, I'd have just seen these. What's the deal? Most of our graphs, if you notice here, go from -10 to 10. That's where I just kind of start looking in that area to see if I can find values. There's a reason behind this one too, though. I'm going to explain both of these here momentarily. But I like to write down all the values I can find between -10 and 10. Because then that's going to allow me to plot more points, which is going to give me a more accurate graph. But with cubes, they keep going forever in both directions. How do I know that? Well, if I keep scrolling in either direction, notice I don't see error messages when I'm dealing with a cubed root. They just keep going. So they never stop, which gives me a big clue on the last part of this too, my domain and range. If things never stop going left or right, they are infinite. If things never stop going down, even though it's slight, down or up, they're infinite. First clue, when you're dealing with cubed roots, they are always going to have infinite domain and range. If there's a stretch, if there's a shift, it doesn't matter. It doesn't matter. Stretch, shift makes no difference at all. It's always going to be infinite. Excuse me for a minute. Must be talking too much. Okay. So, what happens when these do start to shift around, though? How am I going to deal with that? Am I just going to deal with the calculator? Am I going to try and do it on my own? You have some options, okay? First thing you always should do with these is figure out what your transformations are. So here, the transformations. Left 5, down 2. Now we're going to see something here in a minute that I'm hoping you're going to notice. So here's what we're going to do. We're going to pull this up, and I want you to do two things for me this time. We're going to do something a little different. Okay, so second and x squared will give me my square root. Just type in square root of x again for a minute. Okay, we're going to put this up, and I want you to pull your chart back up for a minute. I know we just did this. Oh, error, yeah. Here's what I want you to do. I'm hoping you're going to have two colors, but if you don't, we can make this work. I want you to plot just the points of your parent graph, okay? So we're going to put a dot at 0, 0, a dot at 1, 1, and a dot at 9, 3. Don't connect them. Okay? So with our parent graph, there's a method to the Hardy madness. Just stick with me. Oh my gosh, I lost 4-2. How did I lose 4-2? Oh, it happens. Okay, those are my parent points every time. Now I want to show you something cool. Okay, we're going to go back now, and we're going to type this in, just to let you see how this works. So second x squared to get your square root, x plus 5. Be careful. If you just write -2 right now, I'm going to do it here on ours. Notice it all stays under the radical, and that's not what I want. So let me go back here. When you're done inside the radical and you want to get out, make sure you hit your right arrow one time. Then type in -2. Okay? So now we're going to graph it. And I notice it moved. Where did it move? It moved left. It moved down. So when you pull your chart here, okay, we're still just looking for points that are whole numbers. So -5, -2, -4, -1, -1, 0. Do I have any others coming here? Okay, and 4, 1. You're like, okay, Hardy, what are you trying to get to here? Here's what I'm trying to get to. Let's plot these. If you have a different color, even if it's like a blue pen or something, red pen, that's great. Let's plot these. So -4, -1, -1, 0, 4, 1. We're going to connect them in a minute, but I want you to check on something first for me. Okay? I want you to go to your original parent point dot and go left 5 and down 2. Go to your next point that was in that. Go left 5 and down 2. What? Go left 5, 1, 2, 3, 4, 5, and down 2. You'll never guess. 1, 2, 3, 4, 5, 1, 2. If you know, okay, if you know your parent points, 0, 1, 4, 9, 0, 1, 2, 3. They have something else in common we're going to chat about here in a second. If you know those every time, you can plot these graphs without the calculator. Now, does it mean that you can't use the calculator? No. I'm not going to give you a no calculator test. But it allows you to see what they are. But these numbers, these x numbers in my parent graph also have something in common. 0, 1, 4, and 9. I've seen those somewhere before. Oh, yeah. They're perfect squares. So my x's are just perfect squares between 0 and 10, and y is the square root of them. Now again, am I telling you that you have to know this little pattern? No, but it makes it a lot easier so you're not having to mess with the calculator all the time. Use your best calculator in the world, this right here, between your ears. So what's that going to do to my domain and range? Okay, well, let's see. Where does my graph start x-wise? Right here. If I go back up to the x-axis at -5, it goes forever to the right. You're like, okay. And then my range, my y's, same point it starts at, but it's the y value at that point, which is -2. It's going slightly up forever. You see what I see? There is a direct connection between the transformations in your graphs and their domain and range. If there are no transformations, these stay at 0. So like if it would have just been left 5, that would have started at 0. If you look back and flip back to the last page, we had 0 to infinity, 0 to infinity. There were no shifts, no transformations. But these are always going to match up when you're on square roots. Okay, not on cubed. We already know what the answer to cubed is. But for square, that's what's going to happen. Now, as far as cubed roots go, same idea. Left 2, up 1. You're like, Hardy, is that same thing going to go on this one? Where if I know my parent points, okay, so if this is just the cubed root of x, you're like, okay, Hardy, since before you said these were all perfect squares, are those perfect cubes? They are. Okay, now again, if you don't know your perfect cubes and stuff at this point, don't worry. Okay, you've still got your friend here. The calculator can still help us. But yes, it's going to work the same way as the last one did. If I plot those 5 points to start every single time I'm graphing one of these, I plot the 5, okay, I leave it alone. And then I go in. Here, we're going to do it the opposite way this time. We're going to do all of our mental stuff here first, and then I'm going to put it on the calculator. I'm going to go left 2 and up 1. 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 Okay. This is going to be my graph. Now, let's pull the calculator now. You're like, ooh, now what's this going to look like? How does this work? Okay. When I'm going to plug this in, this whole thing's under the radical. So I'm going to put that part, x plus 2, in parentheses. And just like we did on our original one, I'm going to do it to the exponent over root, the 1/3 power. And then make sure when we do our plus 1, we right arrow first so it's not up in the exponent. Okay? So here's my cubed root of x plus 2 plus 1. Now, if I graph it, it's still going to look like the snake that it always did. It didn't really change anything. But notice, it's not going through the middle anymore. It's shifted left and up. And if I look at my chart, let's look and see if the points end up being the same. So let's see. -10, -1. -3, 0. -2, 1. -1, 2. And 6, 3. Okay, and we'll jot those points down here. Just again, you're seeing there's multiple ways to do this. It's not that you have to do it the Hardy shift around way, or you're bad at this, or anything like that. It's just, forgot my point. I think I'm at 1, but I want to make sure. Okay, -1. I just like giving you options. But even with all of our options, and that we shifted this left 2 and up 1, doesn't matter. Domain and range still are always infinite on cubed roots. Cubed roots. Just something to keep in mind. So really the only thing with these we haven't spoken about is what happens if I have a transformation in front, a stretch, a reflection. What's that going to look like? How would that change with all the little Hardy tricks that we're talking about? Well, let's see. So I look and I go, okay, transformations, 3 of them this time. Oh, I keep moving my chair and I'm not moving me. Okay. Left 1, up 3, reflect about the x-axis. Okay, this is going to flip. Now, this one might be a challenge when it comes to just doing it in your brain. Okay? Could we try? Sure, we could. Okay? If you're going to do it that way, you would plot your 0, 0, 1, 1, 4, 2, to 9, 3. But now, this would get a little trickier because you would go left 1 and up 3, but I wouldn't put my dot there. I would reflect that, which means if I'm at -1, 3, I would come down here, okay, and put my dot. If I'm at this dot and I went left 1 and up 3, okay, I would reflect that down to here. That's why at this time I'm going to show you on here first, and then we'll see if you want to deal with this or not. Okay, that is a negative. Like we've said before, negative is down here, so we'll start with the negative. Second x squared, oops, let me get out of the glare for you. X plus 1, right arrow. Oops, not just 3 though, already plus 3. Okay. And we look at the graph and we see that it opens downward. Did I put my... Yes, I did. I reflected it. Okay. So let's look. So I've got -1, 3, 0, 2, 3, 1, 8, 0. Okay, and that keeps us in there. All right, make sure I typed everything in right. Yes. Okay. So -1, 3. Let me do this with this. 0, 2, 3, 1, and 8, 0. So what actually happened? This might be an easier way to look at it as well. If I start looking at these, I went left 1 and down 3. It's like things just changed. So I'm like, is there a good way to do this with my little trick from up above? I would probably suggest for most of you at this point that I would stick with the calculator just to keep my life simple, okay? Because what you would actually do, and I didn't do with my original points, are I would need to have made my original points the reflection. Then I could have just gone left 1 and up 3 from them. So that was my mistake. See, even the person who's done this forever sometimes doesn't think through this properly and gets themselves into trouble. So I will try and do a better job of remembering that on number 4 here, because that would have made our lives much easier. Domain and range, what happens? Ooh, now that I want to make sure we stay on the calculator for a minute, just to remind us of some things. Okay, domain, x's. Where does it start? Right here. What's the x value right here? -1. And for my range, my y's, same point, but again, it's the y value at that point, which is 3. Now, not a coincidence. The first pair of points that we found right after the error message, okay, first pair, domain, range, x, y. Not a coincidence. Okay, not a coincidence at all. That's how that's going to work. And so the same thing's going to happen on 4. Now on 4, again, transformations. Be careful. The -4 is outside the radical. That's not a left-right. That's an up-down shift. So down 4. We're stretching it by 2. Okay, it's going to stretch more than it normally would. So again, I would suggest, and we're going to write this out this time. If I was going into my calculator, again, exponent over root. And as we do that, let's actually get it in here. Make sure, again, you right arrow so you don't end up with -4 up in your exponent, because that would be a different graph. Okay, it's still going to look like the snake, but now the snake's kind of stretching out and expanding, and it also shifted downward. So again, when you're looking for your points, what we're basically doing here is just going for good old whole numbers as best we can. And usually with cube roots, normally you're going to be able to find 5. It may only be 3 sometimes, but most of the time it's not. So I get those points in. Oops. Got to get your point in the right place. That is important. Okay, wider of a stretch. Again, if I'd have been looking at my parent points, I would have had to have stretched those 2. And for an intro lesson, don't necessarily want to go down that road. I love sharing things, but sometimes I just got to know when to cut it at the start here. So, okay, lessons learned here. Our base graph can tell us a lot. The shifts, left, right, up, down, have not changed from the absolute value graph. And let your calculator be a bit of a guide on this, okay, to get your points. But you can start making some of those connections. So you've got some practice going over here. Again, domain and range and transformations, doing some sketching. Yes, Hardy boneheaded and put the same worksheet in twice. Okay, but that's the end, and we're at the end of this unit. So we'll be getting some info to you here on getting ready for the Unit 2 quiz, and also how to start getting prepared for our Unit 3 stuff, which we'll have to get packets out for. So we will see you then, if Hardy can figure out